Inshallah, in this tutorial, we'll solve about different concepts like the atomic packing factor, the density of the BCC structure and crystal structure and FCC structure. We'll focus in this tutorial, inshallah, mainly in BCC and FCC. Next tutorial, maybe we'll solve about the HCP structure. Okay, so let's start with the first question. The question says, if the atomic radius, so we have atomic radius, we assume always when we talk about atoms that it is like spheres. Okay, it has the shape of the sphere. Okay, and we assume it is a hard sphere. Okay, so when we draw atom, we will draw it similar to sphere. And in this question, he said the radius of the sphere represented by R, okay, capital R, of aluminum. So the element is aluminum is 0.143 nanometer. Okay, so R is equal to 0.143 nanometer. Okay, calculate the volume of its unit cell in cubic meters. Okay, the volume, all of us know the volume, and he said in cubic meter, so I want to calculate the volume. Okay, and the unit is meter cubed. But for what? For the unit cell. So what exactly the unit cell? Yani what is the shape of the unit cell? Yani I want to calculate the volume. The volume is for cube, or it is a cylinder, or it is a sphere, or what? Okay, based on the element given, okay, you can decide. Aluminum, if you see the periodic table, okay, aluminum has this color, which is metal. Okay, all metals have a crystalline structure or a crystal structure. We call it a crystalline material. Okay, crystalline material in which is one in which the atoms are situated in a repeating or periodic array like this. And as you can see, the atoms are repeated in a periodic array. They are repeating themselves in an arrangement, okay, over large atomic distance that is long range order exists, such that upon solidification, the atoms will position themselves in repetitive three-dimensional pattern. So as you can see, there is three-dimensional pattern, and the atoms will repeat itself, okay? This shape or this structure, we call it a crystal structure. All metals, many ceramics, materials, and polymers have this shape, okay? So whenever you see an element which is metal, you will assume it has a crystal structure, okay? A crystal structure, the definition of crystal structure of the material is the manner in which atoms, ions, or molecules are spatially arranged. يعني ازاي بتترتب في الميكانيا يعني تمام. عادة احنا بيكون عندنا crystal structure كبير. We have a large crystal structure. I said for a long range order structure, okay, the atoms will be arranged. It is more convenient that we take a small portion of this whole crystal structure and study it, okay, because it will be repeated again, okay. In describing crystal structure, it is often convenient to subdivide the structure into small repeat entities called unit cells, okay. So if I take, for example, let's assume first right now that the aluminum has unit cell which is cube. If I repeat this cube, okay, again and again and again, I will have the total crystal structure, okay? So in order to take a good imagination of what unit cell is, I prefer to watch the video that I sent on WhatsApp, okay, first. Then we can solve questions because all the questions contains different unit cells, okay? Let me know if you can hear the video or no.
If you could travel within a crystalline solid, you would see the particles,
Okay, تمام.
atoms,
جميل.
ions, or molecules arranged in a regular array. Here, the spaces are greatly exaggerated, but in reality, the particles are packed close together. The unit cell of a crystal structure is the smallest portion that defines the structure. Stacking unit cells next to each other in all three directions gives the structure. Many elements and simple compounds have unit cells from the cubic crystal system. Let's examine the three types of cubic unit cells. All cubic unit cells have particles at the corners of a cube. The simple or primitive cubic unit cell has particles at the corners only. In reality, the particles lie as close to each other as possible. Note that the particles touch along the cube edges, but not along a diagonal in the face or along a diagonal through the body. By slicing away parts that belong to neighboring unit cells, we see that the actual unit cell consists of portions of the particles. When the cells pack next to each other in all three dimensions, we obtain the crystal. If we fade the others out, you can see the original group of 8 particles within the array and the unit cell within that group. We find the number of particles in one unit cell by combining all the particles' portions. In the simple cubic unit cell, 8 corners, each of which is 1/8 of a particle, combine to give 1 particle. A key feature of a crystal structure is its coordination number, the number of the nearest neighbors surrounding each particle. In a simple cubic array, any given particle has a neighboring particle above, below, to the right, to the left, in front, and in back of it for a total of 6 nearest neighbors. The body-centered cubic unit cell has a particle at each corner and one in the center, which is colored pink to make it easier to see. With full-size spheres, you can see that the particles don't touch along the edges of the cube, but each corner particle does touch the one in the center. The actual unit cell consists of portions of the corner particles and the whole one in the center. 8/8 give 1 particle, and the one in the center gives another for a total of 2 particles. In this tiny portion of a body-centered cubic array, you can see that any given particle has 4 nearest neighbors above and 4 below for a total of 8 nearest neighbors. The face-centered cubic unit cell has a particle at each corner and in each face, which are colored yellow here, but none in the center. The corner particles don't touch each other, but each corner does touch a particle in the face, and those in the faces touch each other as well. The actual unit cell consists of portions of particles at the corners and in the faces. 8/8 at the corners gives 1 particle, and half a particle in each of 6 faces gives 3 more, for a total of 4 particles. In this tiny portion of a face-centered cubic array, notice that a given particle has 4 nearest neighbors around it, 4 more above and 4 more below for a total of 12 nearest neighbors. Stacking spheres shows how the 3 cubic unit cells arise. Arrange a layer of spheres in horizontal and vertical rows. Note the large diamond-shaped space among the particles. Placing the next layer directly over the first gives a structure based on the simple cubic unit cell. Those larger spaces mean an inefficient use of space. In fact, only 52% of the available volume is actually occupied by spheres. Because of this inefficiency, the simple cubic unit cell is seen rarely in nature. A more efficient stacking occurs if we place the second layer over the spaces formed by the first layer, and the third layer over the spaces formed by the second. That simple change leads to 68% of the available volume occupied by the spheres and a structure based on the body-centered cubic unit cell. Many metals, including all the alkali metals, adopt this arrangement. For the most efficient stacking, shift every other row in the first layer so the large diamond-shaped spaces become smaller triangular spaces, and place the second layer over them. Then the third layer goes over the holes visible through the first and second layers. In this arrangement, called cubic closest packing, spheres occupy 74% of the volume. Note that it is based on the face-centered cubic unit cell. Many elements, covalent compounds,
So from this video, we can see that for metals, we have different unit cells or different crystal structures, like simple cube, okay, and FCC and BCC, okay. Now, in order to calculate the volume or to calculate everything, we need to know what is the crystal structure. Is it BCC, BCC, or HCB, or any one of them? Okay. In order to know this, we need to know only the element. We have here aluminum. Okay. In the slides, you have under each type of crystal structure, you have different elements as examples for this crystal structure. Also, we have the table 3.1. We can see that aluminum has the crystal structure FCC. Okay. Based on this, we will assume that is the unit cell. Okay, the unit cell contains a quarter of atom at each corner. Okay, and we have a half atom at the face of each at each face of the cube, and we have 6 faces. Okay, so if we say that we have quarter atom of atom at each corner, and we have 8 corners, plus we have half atom at each face, and we have 6 faces for the cube. So we'll have 3 plus 1, we will have 4 atoms. That is the unit cell for the face center cube. Okay. Now in the question, he asked for what? For the volume. Okay. So in order to calculate the volume for the cube, we know that it is cube at the end. It is a cubed, or the side one side of the cube. Okay, one side of the cube, and it is cubed. Okay, a times a times a times a. But in the question, he didn't give me the value of the length of the edge of the cube. Okay, what is given is the atomic radius, r. So I want to make a relation between r and the length of the edge. Okay, I want to make relation between r and a. In order to make relation, if you remember in the video, he was mentioning that they are closed back in one direction at the face, in the face body center cube. And when he draws a simple cube, okay, he said that at the edge, it is the atoms are connected, but in the middle there is no atoms for the simple cube. Okay, but here for the face center cube, it is called face center cube. Why it is called face? Exactly because there is no void here. The atoms are touching each other at the faces. Okay, so in order to calculate or to make a relation between the length of the edge of the cube and the atomic radius, we need to take the face, one face of the cube, and make this relation, because one face we can draw, we can say that this one will represent r, one radius, okay, and this the half sphere will represent 2r distance, or 2 radius, okay, and this one will represent r radius, okay, one only, okay. So we'll have along the diagonal of the face, we will have 4r, okay. And I want to make relation between this line, the most dense line, or the line that has no void in the FCC structure. Okay, relation between the R and A. I know that the edge length is A. This one is A. This one is A. We will call it A, and this one also is A. Okay, I can use the Pythagorean theorem and say A squared 4R squared equal to a squared plus a squared, okay, in order to make a relation between the radius and the edge length, okay. So we'll say that a squared plus a squared, okay, a, and this one is 4r, okay, is equal to 4r all squared, okay. So this will equal to 2a squared, and after the square, it will be 16r squared. Let's divide by 2. We'll have a squared equal to 8r squared. And to take the square root, in order to have only a, we will have a equal to 2 square root of 2 r by the calculator, okay? That is the relation between a and the radius, okay? For the face centered cube. For the body centered cube, we will have another relation, okay? And what is asked from us in the question is to calculate the volume of the cubic unit cell. VC is equal to A cubed. Okay, I already have that A is equal to 2 square root of 2 times R, and I have the value of R given the question, which is 0.143 nanometer. Okay, but he asked to calculate the volume in meter cubed. Okay, not in nanometer cubed. Okay, I know that nano is equal to 10 to the power negative 9, so I will replace the nano by 10 to the power negative 9. So we will say that VC is equal to A cubed, and already A cubed is 2 square root of 2 times R. Okay, all cubed. Now I will replace only R. Okay, 2 times square root of 2 times R, which is 0.143 times 10 to the power negative 9. You have to convert it to meter cubed. Okay, and this will give you that the volume is equal to 6.62 times 10 to the power negative 29 meter cubed. That is for the first question. Okay, if you have any questions regarding this problem, you can ask, and you can interrupt me in any time يعني, while I'm solving. If there is no questions, class, we will continue to the next question. Here, he said, show for the body center cubed. So he told me that I have a BCC structure, crystal structure, that the unit cell edge length A and the atomic radius R are related through 4R over square root of 3. Okay, I want he wants for me to show him that this relation exists, or this relation is true. Okay, he said that it is a body center cubed. I know that is the unit cell for the body center cubed. I have a quarter of atom at each corner, and I have 8 corners. Okay, and I have a whole total 1 atom inside the unit cell or inside the cube. So I have 1/8 over times 8 corners. Okay, plus, and I have this atom inside the cube. So I will have 1 plus 1. At the end, I will have 2 atoms for the body center cube. We say that for the FCC, when you calculated the number of atoms, we have 4 atoms. Okay, 1 because of the corners, and I have 6 faces. Each one has half atom, so I will have 4 atoms. Okay, this photo before we slice the atoms and obtain this shape. That is the unit cell. That is the shape of unit cell. The whole shape of this is the crystal structure, and it consists of many unit cells. Okay, in all the directions. Okay, in order to show him the relation, I also need to find the direction that has no voids. Okay, that is the atoms, or all the atoms are connected together. In the face center cubed, we take one of the faces. Okay, we take this face. Okay, and we take the diagonal of the face. Here, if I take the diagonal of the face, I will have void at this place, or I will have void at this place. So I cannot take the face and make the relation and find the relation between R and A. I need to find the direction that contains no voids, which is the diagonal of the cube. I will start from this point, okay, and I will go to this point, or from here, from this point, and I will go like this to this point. Okay, so if I draw a cube by myself like this, I want to go from this point, let's call it A, to this point, which is let's call it B. Okay, I want to go like this because I will pass through this quarter, and then I will pass through this entire atom inside the cube until I will reach the another corner, the opposite corner here at the end of this corner. Okay, in order to find this one, I need also to use the Pythagorean theorem. So I need to make a right angle triangle. Okay, so in order to make a right angle triangle with this direction AB, with this line AB, I need to take one diagonal of one of the faces and one side of the cube. I need to take this line. Let's call this point C. So I want to take this line at the bottom, okay, at the base, and the one side of the or one edge of the cube. Let's call let's call. We know that we usually call it A. Okay, so and in this line from A to B, I will have one R, and I will have also 2R for this big blue atom, and I also will have another R here for this quarter at the corner. Okay, so I will have also 4R. So I can say that the line AB is equal to 4R, or the radius times 4. Okay, and the line BC is the edge of the cube, so it is A, only A. Okay, the remaining is to calculate AC. I know also that this edge of the cube is A, and this also is A. Okay, I can make Pythagorean theorem like what we did in the FCC structure. Okay, in order to calculate the AC. So AC squared. Okay, if we make the Pythagorean theorem for this again the triangle, it will be equal to A squared plus A squared. This one squared plus this one squared will give you AC squared. So AC squared is equal to 2A squared. Okay. Now I know the value for AC. Okay, I know the value for AC, and also I know the value for BC, which is A only. I need to calculate AB in terms of A. Now I already know AB in terms of the radius R. I also need to know its value in terms of A. Okay, so AB squared, if I make the Pythagorean theorem, it will be BC squared plus AC squared. Okay. And already I know that BC is equal to A, so if BC squared is A squared, and AC squared, already we obtained it from the Pythagorean theorem, is equal to 2A squared. Okay, so at the end, AB squared in terms of A is equal to 3A squared. So I have now AB squared is equal to 3A squared, okay? And also I know that AB is equal to 4R, but here is AB squared. So I need to say that AB squared is 4R. AB squared is equal to 4R squared, and it is equal also to 3A squared. Now I have the relation between R and A. So let's square this one. It will be 16R squared, and it is equal to 3A squared. I will divide by 3. Okay, so I will have that A is equal to 16 over 3R squared, A squared. Okay, and then I will take the square root. If you take the square root, it will give you that A is equal to 4 square root of 3 over 3R. That is the relation between A and R. In the question, he gave me this relation that A is equal to 4R over square root of 3. It is the same like this relation. All what we need to do is to multiply by square root of 3 over the square root of 3. Square root of 3 times square root of 3 will give you 3, and this will be in the denominator. So we can write it in another way like this: 4 times square root of 3. No, it will be 4 times 3. Okay, this one will square root of 3 times square root of 3 will give you 3. And already you have 3 at the denominator. And also here you will have square root of 3. 3 will go with 3. And you have R. At the end, you will end up with the same relation given in the question. Okay, so it will be 4 over square root of 3R. Okay, that is for this question. So now we obtain relation between A and R for BCC, and also we obtain it for FCC, this relation. And you can directly find the volume for FCC and BCC from this relation if you only have the radius. If you have any questions regarding this problem also, you can ask. Otherwise, we'll continue, inshallah, for the next question. Let's continue. The question 3.5. He said show the atomic that the atomic packing factor for BCC is 0.68. So we know that the atomic packing factor. What is the atomic packing factor already? atomic backing factor, he gave me that it is equal to 0.68 for BCC structure. BCC structures like this unit cell. Okay, the atomic backing factor is the sum of sphere volumes. Sphere, we said that we represent atoms as spheres. Okay, so it is the sum of all the sphere volumes. Okay, we have atoms, and each atom has a volume. Okay, so the volume of one atom times the number of total atoms will give you the total volume of all atoms within a unit cell. Okay, so here he said BCC. Okay, we know that for BCC we have only 2 atoms. Okay, 1/4 times 8 plus the atom inside the cube, so I'll have 2. Okay, so I know the number of atoms is 2. Okay, and I know that we will represent atoms as spheres. Okay, and the volume for one sphere, volume for any sphere, one sphere, we know that it is equal to 4/3 pi r cubed. Okay, so I will only multiply the volume of one sphere times number of spheres or number of atoms, which is 2, in order to get the total volume of the spheres or the atoms. So it will be Vs. Let's say this numerator is represent Vs, a volume of atoms in unit cell. That's what he was talking about, the numerator. 2 times 4/3 pi r cube. Okay, the atomic backing factor is the sum of the sphere volumes of all atoms within a unit cell. Okay, this is the unit cell. The atoms inside the unit cell for BCC is only 2 atoms, and the volume for one atom or for one sphere is 4/3 by r cube. So I multiply 2 by 4/3 by r cube, divided by the unit cell volume. We know that the unit cell volume, the unit cell is a cube, so the volume of a cube is a cubed. Okay, that is the edge length cubed. Okay, but I don't have the the value of a cubed. Okay, so what we'll do that already we can make the relation, or we already obtained the relation in the previous questions. We said that VC is equal to a cubed, and from the previous relation or the previous question, we found that the relation between R and A for BCC is equal to this value. A is equal to 4/√3r. Okay, so I will take this relation. I will replace A with 4/√3r here. So it will be like this: 4/√3r cubed, and this will give you at the end 64 times √3/9 r cubed. Okay, so that is the volume of the unit cell. Okay, and so I have the numerator, the volume of the atoms or the spheres, over the volume of the unit cell itself. Okay, the volume of the unit cell itself already it is the cube. Okay, and the atoms are inside the cubes, but there is voids. So the atomic backing factor is the ratio of how much atom that you have in a unit cell. Okay, so I will divide that Vs over Vc in order to obtain the atomic backing factor. Atomic backing factor is equal to Vs over Vc. Vs is number of atoms, 2 times the volume of any sphere, which is 4/3 pi r cubed, over the volume of the unit cell, which is 64 √3/9 r cubed. I will cancel r cubed with r cubed. Okay, and the remaining is constant. This will give you 0.68, and by this we showed that the atomic backing factor for the BCC structure is 0.68. Okay, so that is it for this question. Let's see the next question. The next question said that we have iron, which is Fe, okay, has a BCC crystal structure. So he gave me the crystal structure, and I know the unit cell that it is BCC. Okay, an atomic radius of 0.124 nanometer. Okay, so I know the atomic radius R, okay, is equal to 0.124 nanometer. Okay, and an atomic weight of 55.85 joule gram per mole. Okay, So the atomic weight or the molar mass for Fe is equal to 55.85 gram per mole. Compute and compare its theoretical density with the experimental value found inside the front cover. Okay, let's ignore this sentence. Usually you will be given the experimental value in the question in the exam or in the midterm. So already let's say that the experimental value that you will find in the front cover, for the density yani, for the raw experimental is equal to 7.87 gram per centimeter cubed. Okay, I want to calculate the theoretical density. Okay, R theoretical. Okay, the equation for the density is this one. It is equal to number of atoms associated with a unit cell. The unit cell here, he said it is BCC. It's a crystal structure, so the unit cell is BCC. Okay. And we know that for BCC, we have only 2 atoms, as we saw in the previous questions. So I know that N is equal to 2 atoms. Okay. And this one is the atomic weight given in the question. A for the Fe for the iron is 55.85. So I also have this one. And VC is the volume of the unit cell. And we already found the volume of the unit cell in the previous question, which is 64 times square root of 3 over 9 r cubed for the BCC structure. Okay. Only what you need to know is the relation between A and R. Then you cube this relation. You will get the volume for the BCC. Okay. So all the questions will follow the same procedure. You just only have the relation between A and R. You know how to obtain it, or maybe you can memorize it at the end. Yani you will have summary for the relations, the relation between A and R for the FCC, the relation between A and R for the BCC, the ratio between the atomic backing factor, the ratio for what is the equation for the atomic backing factor, and the equation for the theoretical density. Okay. These are the equations that we will use in this tutorial only. Next tutorial, inshallah, will be about directions and planes. Okay, so for this question, we know that the VC from the previous question is equal to 64 times square root of 3 over 9 r cubed. So also I have VC. And in A, the Avogadro number, it is given 6.022 times 10 to the power 23 atoms per mole. Okay. He needs he needs from me to calculate the theoretical density using this equation and to compare it with the experimental value. In order to compare any two quantities, okay, they must be in the same units. Okay, they are both of them are density, but this one, it is given, if you assume it is given in the question, the raw experimental is 7.87 gram per centimeter cubed. So it is per centimeter cubed. What is given in the question that the radius is in nanometer. Okay. So I want to convert nanometer to centimeter in order to have the theoretical density in the unit of gram per centimeter cubed. Okay. What I need to know, what I need to do is to multiply by 10 to the power negative 7. Why? Because 0.124 nanometer. I know that nanometer is equal to 10 to the power negative 9. So if I replace only nano is equal to 10 to the power negative 9. So if I replace nano with 10 to the power negative 9, it will be 0.24 times 10 to the power negative 9 meter. But I don't want the unit to be in meter. I want it to be in centimeter. And I know that to convert from meter to centimeter, I need to multiply by 10 to the power negative 2, to multiply by 10 to the power 2. So I need here to multiply also to 10 power to multiply by 10 to the power 2. Okay. So in multiplication we add the power. So negative 9 plus 2, you will have negative 7. So negative 7, if you multiply directly by negative 7, you will have the unit in centimeter. So it will be 0.124 times 10 to the power negative 7 centimeter. That is the value for the radius. When you want to calculate the density, you have to convert the radius to be in centimeter unit. Okay. So what is remaining is just to apply all these numbers in the equation. Okay. So the equation is N times the atomic weight over the volume times the Avogadro number. Okay, we know that it is BCC structure, so number of atoms is 2. The atomic weight is given in the question 55.85. Okay, and the volume from the previous question is 64 times square root of 3 over 9, okay, times r cubed, okay, so it will be 0.124, and I must put it in centimeters, so it will be multiplied by 10 to the power negative 7, and it is cubed, okay, times the Avogadro number. Avogadro number is 6.022 times 10 to the power 23, okay. Then I will have the density is equal to 7.9, approximately 7.9 gram over centimeter cube. At a 7.9, and we assume that is this one is theoretical. We assume that we already given the value for the experimental, which is 7.87. So if we calculate the relative error, will be 7.87 minus the absolute value for the subtraction between 7.87 and 7.9 over 7.87 times 100. Okay, this will give you 0.3812%, which is very small. Okay, so that is how you can calculate the density for the elements. Okay, here we have another element, which is rhodium or rhodium, I don't know, has an atomic radius of 0.1345 nanometer. So R is equal to 0.1345 nanometer. Okay. And a density of 12.41 gram per centimeter cube. He already gave me the density. Okay. 12.41 gram per centimeter cube. Determine whether it has an FCC or BCC crystal structure. So I want to know, is this rhodium RH has FCC structure or BCC structure? And it is opposite to the previous question. He gave me that it is BCC, and I want to calculate the density. Here he already gave me the density, and he asked if this element has a BCC crystal structure or FCC crystal structure. Okay. So what I need to do is to calculate R for, as I will assume it is, for example, it is FCC, and calculate the rho, and also I will calculate rho for BCC and see which one of them will give me this value 12.41. Okay, the only difference will be in what? The only difference will be that the VC will change, okay, because we know that we obtain a relation between R and A for FCC different than the one for the BCC. So of course, if we say that VC is equal to A cubed, so the relation or the value will be different for FCC and BCC. And for FCC, we have 4 atoms, so N will equal to 4. And for BCC, we'll have 2 atoms, so N will be equal to 2. Of course, they will give me different values. So I just need to know which one will give me 12.41. Okay, so let's calculate for BCC. So rho for BCC will equal to number of atoms, N is equal to 2. The atomic weight, assume it is given in the question. It will be given in the exam, if you have question about this. So the atomic weight for the rhodium is equal to 102.91 gram per mole. Okay. So it is multiplied by 102.91 over the VC. From the previous questions, we found that the VC for the BCC is equal to 64 square root of 3 over 9 times R cubed. And now we said that R must be in centimeters, so I will multiply by 10 to the power negative 7. Okay, so it will be 0.1345 times 10 to the power negative 7 centimeter. Okay, I need it to be in centimeter because the given value here is in gram per centimeter cubed. Okay. So I multiply by R cubed, so it will be 0.1345 times 10 to the power negative 7 cube times the Avogadro number, which is 6.022 times 10 to the power 23. So the density for BCC is equal, if you calculate using the calculator, it will be equal to 11.4046. It is not equal to 12.41, which is given in the question. Okay, so I predict that the crystal structure or for rhodium is FCC, but let's make sure and calculate the atomic density for FCC. So it will be also n for this time. It will be equal to 4, n equal to 4, and atomic weight will be the same, 102.91. Okay, VC. It is we calculate VC for the FCC at the beginning of the tutorial at question number 1, when we already found the relation between A and R. Okay, this relation. And at the end, we said that VC is equal to A cubed. We obtained that VC is equal to 2, or this one will be 2 cubed times 8. Okay. At the end, this one, if you calculate 2 times square root of 2 squared, this one is cubed, and also R is cubed. At the end, you will obtain this value. Let's make sure with the calculator. Yes, it will be 16 times square root of 2 times R cubed. Okay, so I will use this equation to, for VC for the FCC structure. Okay, so only you will have only two relation between A and R, and then you can obtain VC by by taking the cube of the relation. Okay. So here the VC will be 16 times square root of 2 times R cubed. R cubed is 0.1345 times 10 to the power negative 7 cubed, and times the Avogadro number, 6.022 times 10 to the power 23. This will give you exactly the same value given in the question, which is 12.41 gram per centimeter cubed. So we will say that the rhodium has the FCC crystal structure. Okay, it has FCC crystal structure. Okay. If you have any questions, you can ask Yani. We still have only one question remaining. If there is no questions, خلاص we'll continue inshallah. Question 3.20. He said that the combining figure, this figure, shows a unit cell, this unit cell for a hypothetical metal, any metal, okay? To which crystal system does this unit cell belong? Crystal systems, we have, if you saw the slides, you have 7 crystal systems, okay? You have seven crystal systems, okay? Based on the configuration or the dimension of the edges of the cube and the angles, the 7 crystal system will be the crystal system will be different. As you can see here for cube, the BCC, FCC, always we have that the edge length is A, only A, always will equal to A, and the angles is always right angle, 90 degree only. Okay, maybe we'll have a shape that one of the edge is not equal to A, maybe it has another value, maybe one of the angle is not 90, maybe it's 75, like this. So that is the different crystal systems. Okay, so he is asking what is the crystal system for this unit cell. Okay, this unit cell, as you can see, has this edge is 0.3 nanometer, this one is 0.3 nanometer, but this one is 0.4 nanometer. Okay, and all the angles, this one is 90, this one is 90, this one is 90. Okay, all of them are 90. Okay, so if I compare with these 7 crystal systems, I will find that this unit cell is tetragonal because I have 2 edges that has the same length 0.3 0.3. So assume they are A. This one is A and this one is A, and this one 0.40. This one is C. Okay, and the angles, all of them are 90. So I will say that the crystal system for this unit cell is tetragonal. So the answer for part A is tetragonal. Okay, so we decided the crystal system based on only the configuration or only the length and the angles of the unit cell. Okay, for part B, he asked what would this crystal structure be called. Okay, when you talked about the crystal structure in the previous systems, we said BCC, FCC, how the atoms are arranged, right? Here, where is the atoms? I have atom at each corner, okay? Or then it is quarter atom for this unit cell, okay? This atom, so I have 8 atoms here, okay? In each corner, I have 1 atom, okay? And I only have 1 atom inside, okay? What of the previous crystal structure that we already discussed in the previous questions that have atoms at the corners, okay, and 1 atom inside the cube, it is BCC, okay? We said at the beginning it is BCC, okay? But the BCC is cube only, okay? It is the edges of the cube, all of them have the same length, okay? But here we have 0.40. So we will take the word body, okay, and we'll say it is body centered but not cube, it is tetragonal. So it is body centered tetragonal, okay? So the name of this crystal structure is body because I have a unit or I have an atom in the body of the unit cell, okay, centered. It is in the center of the cube, okay, and it is tetragonal because the edges are not they don't have the same length, okay? So it is body centered tetragonal, okay? That is for part B. For part C, calculate the density of the material given its atomic weight is 141 gram per mole, okay? Calculate the density. We know that this is the equation for the density, okay? And we can say that N is also equal to 2 because I have 1/8, okay? You'll take only this quarter or 1/4 of the atom. Is the just because this unit cell will be connected to another unit cell from here and also from the other side, and from the top you will have it is connected. So each the only one unit cell will have 1/8, okay? And you have 8 corners, so 1/8 times 8 corners, and you have this atom in the body centered in the center of the cube, okay, so +1. So at the end you will have 2 atoms, okay? So it is similar to body center cube, but this one is called body center tetragonal, okay? So you will have 2 atoms, and it is given the atomic weight, so A is also given, and VC for this one, we know that VC is equal to A cubed, okay? But this time for the if it is body center, if it is cube only, okay, here we have, I can find A times C, okay, not necessary to say A cube, so it will be, instead of this one, it will be A times C, okay, 0.3 times 0.3 times 0.4. I don't need to find a relation between A and R directly because I already given the dimensions of this tetragonal shape. I can calculate the volume, okay, الطول في العرض في الارتفاع L times W times H, okay? So A times C, okay? So VC will equal to 0.3 times 0.3 times 0.4, okay? But these values are in nanometer, okay? I want to calculate the density usually in gram per centimeter cubed, okay? So I need to multiply by 10 to the power negative 7 for each one of them, okay? So 0.3 times 10 to the power negative 7 to be in centimeter instead of nanometer, times 0.3 times 10 to the power negative 7 times 0.4 times 10 to the power negative 7. This will give you that VC is equal to 3.6 times 10 to the power negative 23 centimeter cubed. That is for this unit cell يعني. Okay, you can say it is per unit cell. Okay, so I have BC, and already the Avogadro's number is given in the question 6.022 times 10 to the power 23. I don't know if you need to memorize it or no, يعني. And also I don't know if you need to memorize also يعني each element, what is the crystal structure. يعني if he give you aluminum, he will say it is FCC crystal structure, or you need to know. So you can ask the doctor about this, يعني if you need to memorize or no need. Okay. So just I will calculate using the equation for density. Okay, so let's say rho is equal to n is two atoms, and the atomic weight is 141. VC is 3.6 times 10 to the power negative 23, and Avogadro's number is 6.022 times 10 to the power 23. So the density will equal to 13 gram per centimeter cube. Okay, خلاص يعني I think I finished the questions for this tutorial. If you have any questions, you can ask if you have anything. You are most welcome. You're most welcome. خلاص إن شاء الله if you don't have questions, I can stop the recording.